What we're going to do in this video is just do a quick recap or summary of what we've done up to this far, looking at the solution of these second order homogeneous linear differential equations, right? And so we've looked at a bit of theory, but I think it would be good to just do like a quick summary of the process so far. So the equations that we're solving are of the form, and this is kind of the general form, a2 y double prime plus a1 y prime plus a sub 0 y, that's equal to 0, and our coefficients, so a2, a1, a0, these are real numbers. Now, we can certainly continue to use this particular form, right? But it's also convenient if we use coefficients that we're used to in terms of coefficients for equations that have three terms. So when you think about a quadratic equation, we normally represent the quadratic equation as, with coefficients a, b, c. So we can actually do that, right? So there's absolutely nothing wrong in doing this. There's no requirement that we have to have a's with subscripts here, but we can write our general second order wholly in this form, right? Just with the understanding that, for one, we don't want the leading term to be equal to 0, right? So we don't want that leading coefficient to be 0. And then, of course, they can all be real numbers, right? So that's one thing. Now, remember, as far as solving this, the first step is always to write down the corresponding characteristic or auxiliary equation. So the auxiliary equation is of this form, and it's simply the quadratic that has the same coefficients as the wholly. So in other words, the coefficients would be a, b, c, but we don't write derivatives anymore. We write powers of some other variable. And in some instances, you might see resources that use r as their variable. We're using m, again, just using a letter that we're likely not going to use in any other context, right? So the auxiliary equation now, using ABC, would be am squared plus bm plus c is equal to 0. And we can find the roots of this, right? Because we know how to solve quadratic equations. So if we end up getting solutions that look like this, either m is equal to m1 or m is equal to m2, where m1 and m2 are different, right? So m1 is not the same as m2, and they're both real numbers. If we end up with this, then we found these two special functions that we need. So then a function e to the m1x and the other function y2 equals e to the m2x, they form what we call a basis or a fundamental set for all the solutions to this differential equation. So these two special functions, they form what we call a basis or fundamental set of all solutions, right? So of all solutions. Well, how does that work? Well, there's that theorem that says once you find these two special functions that are not scalar multiples of each other, then the general solution, so now let's write down our general solution to our original second order wholly with constant coefficients. So our general solution is, it's y equals, and the theory says you take every possible linear combination of these two functions. So c1 times y1 plus c2 times y2, and that ends up being c1 times e to the m1x plus c2 times e to the m2x, right? So this kind of summarizes the process, And nothing works better in a summary than actual examples. So let's do a few examples of this. Again, just to really focus on the process and why we're doing what we're doing at each step. And in each case, we'll go ahead and either find the general solution or a particular solution. So let's take a look at our first example. And let's say we have y double prime plus 11y prime plus 24y is equal to 0. And let's say we have a couple conditions, right? So a couple initial conditions. So y of 0 is 0, y prime of 0 is negative 7. All right? So first we're going to write down our auxiliary equation. And that, in this case, is going to be m squared plus 11m plus 24. That's equal to 0. Then we have to ask ourselves, can we, we have a quadratic now, can we factor this? And this one is factorable. If you look at it closely, you have m plus 3 times m plus 8, right? So that's the factorization. So right away, we see that we do end up with two real distinct roots. So m1 is equal to negative 3. Let me fix that. So m1 is negative 3, and then m2 is equal to negative 8, right? So here is our basis or fundamental set. So I'm just going to call it basis, and that consists of these two functions. I'll write it as a set because technically a basis is a set. So it's the function e to the negative 3x and the other function e to the negative 8x, right? And then from these two specific functions, we can now create all the possible solutions to this. So from this, we can write down our general solution. So our general solution, based on that superposition principle, it says y can be or has to be of the form c1 e to the negative 3x plus c2 e to the negative 8x. So if we were not given initial conditions, this would be our answer to this second order Goldie, right? Now, if we want to find the particular solution that's satisfying this these two initial conditions, or this set of initial conditions, well, if you notice, one condition uses y, which we already have. The other condition uses y prime. So in order to apply this second condition, I will need to find y prime. So let's go ahead and differentiate this. And to find this derivative, we're going to have to remember our rule for exponential functions as well as our chain rule. So finding the derivative here, we're going to get negative 3c1 e to the negative 31x minus 8c2 e to the negative 8x. So now if I take this first equation, the general solution for y, and apply this, this tells me that when x is equal to 0, y is equal to 0. So plug 0 in for y and 0 in for all the x's, then we're going to end up with this equation. c1 plus c2 is equal to 0. Similarly, take this y prime and apply the second condition. So the second condition says that when x is equal to 0, y prime is equal to 7. So let's do the same thing, or negative 7. Right, so replace all the x's with 0 and replace y prime with negative 7. Now we end up with this second equation, negative 3c1 minus 8c2 is equal to negative 7. Now, here we have a linear system, and we're solving for these coefficients, c1 and c2. This is a pretty familiar thing. How can we solve this? Well, you can use any method you want. You can use some of the more formal matrix methods that we've looked at, or we could just use a simple substitution. So we could say from this that C1 has to be negative C2, and then just substitute negative C2 in for C1 here and see what we get for C2. So if I substitute, so basically I am plugging this in right here, and then that gives me a positive 3C2 minus 8C2 is equal to negative 7. So then negative 5C2 is equal to negative 7. So C2 has to be 7/5. And then if C2 is 7/5, then C1 is simply the negative of 7/5. So C1 is negative 7/5, right? And again, we don't circle this, right? We want our function. So in this case, the function, and it is guaranteed to be a unique function because of that existence and uniqueness theorem. So the unique function that satisfies not only this differential equation, but also this pair of initial conditions is this. So here is our particular solution. And in this case, it's now, so yeah, just plug your C1 back here, plug your C2 back here, and then in fact, I'll write it very formal. So our function y of x is negative 7/5 e to the negative 3x, and then plus 7/5 e to the negative 8x, right? And that's our solution. Now, again, when you kind of look at this, you're like, really? I mean, is that what the process entails? And yes, this is what it entails. Recognizing we have one of these special second order wholes with constant coefficients, finding the roots of the auxiliary equation, identifying our basis. Now, it's not necessarily something that you have to state formally, but it's good to keep in mind that it's based on these two linearly independent functions and using that superposition principle. Right here is where we use our superposition principle that tells us once you find two, right, linearly independent functions. How do we know that they're linearly independent? Well, they're not scalar multiples of each other, right? So once I have these two linearly independent functions that solve or satisfy the differential equation, the superposition principle says I can take all possible linear combinations of these two functions and get all possible solutions to this differential equation. Very powerful, going from two to what essentially is infinitely many, right? And then if we have conditions, then we can identify which of all of these satisfy not just the differential equation, but the initial conditions. All right, let's do one more example before we wrap this video up. And it's always nice to see you have examples. So let's look at our second example. Let's say we have 4y double prime minus 5y prime is equal to 0. And we have y of negative 2 is equal to 0, and y prime of negative 2 is equal to 7, right? So a couple interesting things will come up in this solution. For one, you notice that we only have two terms, right? So we only have a second derivative and a first derivative term. We don't have just the y term, but that's fine. It just means that that coefficient is 0. So the auxiliary equation for this is 4m squared minus 5m is equal to 0. We can factor out an m, and we will have 4m minus 5 as the remaining factor. So then here are our two real distinct roots. So 0, which can work, right? Or 5/4, right? So based on these two roots, we can write down our basis. And in this case, it's the function e to the 0x and the other function e to the 5/4 x. Well, e to the 0x, actually that's just a constant. So it's just 1, right? And then we have, of course, we have the e to the 5/4 x, right? And this can happen. It can happen if one of your roots, right, happen to be 0, then yeah, we're going to end up with e to the 0x, which simplifies to 1. So let's write down our general solution. So the general solution, it's every possible linear combination of this and this. So it looks like this. It's C1 times 1 plus C2 times e to the 5/4 x, right? And that's it. Now, we don't have to write c times 1. I'm just going to simplify that as c1. And then we have c2 e to the 5/4 x. All right. So that's our general solution. Now let's see if we can find the function that satisfies the conditions now. Which particular one satisfies this condition? Now, probably 99% of the time you'll get initial value problems where the initial value of your independent variable is 0. But it doesn't have to be, right? In this case, for whatever reason, the initial value is of x is at -2. But let's see how that works. Regardless of what the initial value of x is, we are going to need the derivative. So let's differentiate our general solution. So y prime, that's equal to, now what's interesting about getting something like this is because this is just a constant, when I differentiate it, the c1 completely goes away. So c1 doesn't even show up in our derivative, right? So what we're left with is the derivative of this term, which is 5/4 c2 e to the 5/4 x, right? So now let's apply these two conditions and see what we get. So when x is equal to -2, y is equal to 0. So that's our first condition here. So what does that tell me? Well, I would have to plug -2 in for x here. So we have c1 plus c2. Now when I plug -2 in here, the e doesn't go away, right? So I'm going to have to keep the e, but keep in mind that it is a constant. So it's c2 times e to the, now 5/4 times -2 is -5/2, and then that has to be equal to 0, right? Okay, so that we can't really do much with this, right? Because there are two constants, but just one equation. But then let's use the other condition. Let me write it down, and then I can scroll. So when x is equal to -2, y prime is equal to 7. So now use this equation, right? So we're going to plug -2 in for x. So we're going to have 5/4 c2 e to the -5/2, and that's equal to 7. All right. Well, what I can do is I can solve the bottom equation for c2 and then substitute it into the top equation and solve for c1, right? So how do I isolate c2? Well, I'm going to multiply both sides by 4, divide by 5, and then divide by the e. And let's do it in stages so we don't get too lost in the algebra. So first dividing both sides by 5/4, or you could say multiplying both sides by 4/5. This is what we will get, 28/5. And then dividing both sides by the e, what that's going to do is that's actually just going to change the sign of the exponent. So c2, so therefore c2 is 28/5e to the -5/2. No need to have this negative exponent. We can actually make it a positive exponent by taking the reciprocal. So this is 28 fifths e to the 5 halves. All right, so that's C2. And then look at what C1 is going to be. C1 is going to be the negative of C2 times this E, right? So, and C1 is negative of this 28 fifths e to the 5 halves times e to the negative 5 halves. Right? But then when I multiply these two, because the bases are the same, I add the exponents, I'm going to have e to the 0. So I end up getting negative 28 over 5 e to the 0, which is negative 28 over 5. So now I can write down what my particular solution is. So the particular solution is y equals, here is C1, negative 28 over 5, and then plus C2, here is C2, so plus 28 over 5 e to the 5 halves, but then it's times e to the 5 over 4 x. And I can certainly leave it in this form, but what I'm going to do, use another property of exponents, in fact the same property that I used here, use it again, and because I'm multiplying two exponential expressions where the base is the same, I can add the exponents. So therefore, here's my nice and formal way of writing down my particular solution to this second order initial value problem. We have negative 28 over 5, and then plus 28 over 5, and then I'll have e, and then I'm going to write this as 5/4 x plus 5 halves. Right? And there's our unique solution, again guaranteed by our existence and uniqueness theorem. Right? So I think that's the kind of summary or the recap that I wanted to go through in this particular video. Just again, I know like sometimes when you see it at first there's a lot of theory and so forth, but when you look at it just from a process standpoint, it is very straightforward. And then what we're going to do in subsequent videos is look at what happens when we have different types of solutions to our auxiliary equation. Because right now we only have a procedure in place for handling when we have two real distinct roots. What happens if we have a real root, but if it's repeated? And what if we end up with two complex conjugate roots? So we have to learn how to handle those complex numbers. So if you want to see how to do that, jump over to the next video. I'll see you there.